is sine of r if k is plus 1, it's r if k is 0, and it's hyperbolic sine if k is minus 1. And so you get a factor there in which the spatial geometry is changing the apparent size of this object out there. Now, additionally, the scale factor was different. We're looking down the light cone from here, where the scale factor was large, to there, where the scale factor was smaller. And to work that out, we've got to work out this expression here. But, sorry, what I should have also said is, of course, we have to work out r, which is the integral dt, integral from the time of emission to the time of observation dt over a of t, which is the formula that I worked out there. Now, you can do this two ways. You can take a particular solution and put in the function and work it out, or you can rewrite that as the integral at the scale factor at the time of emission, scale factor at the time of observation, dA over a dot, and then so what you do is you change variable from t to a, and so what happens is the a goes through, and then dt becomes dA over a dot, and then you substitute that from the Friedmann equation, because the Friedmann equation gives you a dot squared. And so what happens here is the matter, whatever matter you have chosen, feeds into the Friedmann equation. The Friedmann equation feeds in and determines a dot as you go down the light cone. This integral then tells you what this function r is, and you put it in there, and you get the apparent sizes. And that's quite a complicated kind of procedure. But it gives you a very nice formula, which is written down here, Matik's formula, area distance, for the case of p is 0 and lambda is 0, the simplest cosmological models. Go through this, and you can do it exactly. And what you get is what is written down here, 1 over h0, q0 squared, 1 over 1 plus z squared into q0 z plus q0 minus 1 into square root 1 plus 2 q0 z minus 1, close the brackets, close the bracket. It's a somewhat complicated formula, but from this you can plot the curves of area distance as a function of redshift. I've used the word area distances because given that we're in a Robertson-Walker, if lengths go like that, then areas go like RO squared times solid angle. So lengths goes as RO times angle, and Robertson-Walker model areas goes like RO squared times solid angle. And this formula you can use to plot curves, and you can go out and try and use this. In fact, we heard in Bruce Bassett's talk already how angular sizes are used in cosmology as tests trying to determine Q0. So it's from here, from this equation. Now, the single most interesting thing about this was discovered by Fred Hoyle in 1960, and that is that there is a maximum to R0. Now, that was quite unexpected until Fred Hoyle actually worked this out. What does it mean by saying there is a maximum? What it means is, if you take an object of given size and move it away, it looks very large to begin with, it looks smaller and smaller, and then it starts looking larger again. That is the apparent size of an object of given size as you move it down to higher and higher redshifts. As you move it down, its apparent size gets smaller and smaller, reaches a minimum, and starts getting larger. Wow, what's happening there? Well, what's happening there is our entire past light cone is getting refocused by the gravitational field of the universe. The light is moving out, and the whole light cone is refocusing. What is happening? The distance between two null geodesics is reaching a maximum and then is starting to decrease again, because all of the gravitational matter in there is pulling the light in and is causing the entire universe to act as a huge gravitational lens. And this is really quite exciting, because you can now say, look, for very, very distant objects, they're going to look much larger than you would have thought if you had used your naive expectations of Euclidean geometry. And so, in fact, you can do a little calculation, and in the simplest case, for the Einstein-de Sitter universe, the redshift at which this happens is 5/4, 1 1/4. 1 1/4 is 5 × 10⁻⁴. 1 × 10⁻⁴. 1 × 10⁻⁴ is 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 1 × 10⁻⁴. 1 × 10 What that means is, in the standard Einstein de Sitter model, which is a pretty good model of the universe in recent times, anything beyond a redshift of 5 1/4 is looking much larger than it should have done. In fact, for any model beyond there, it is looking the same size as something much nearer. And you might spend a few moments thinking about the following. The furthest we can see is the surface of last scattering. And there is a huge amount of refocusing by the time we hit the surface of last scattering, which means if you have a rigid rod down there, it looks the same as something really quite close. You might like to do as a little exercise. What is the redshift at which the angular size at the surface of last scattering is the same as an object which is actually really quite close to us? That's actually quite a nice little calculation that you can do. So area distances refocus. And they refocus quite close in a Einstein de Sitter universe because by today's standards, that's actually quite close. Now, the third thing is luminosities or intensities. And what you have to do there is turn around your thinking. What you have to do there is think, here is the galaxy, and the galaxy is emitting light which is coming up, and here I am the observer, and my world line intersects there. And what we need to think of is this galaxy is emitting light in all directions. We've put a telescope up here, telescope of a certain aperture, and what that telescope does is it cuts off a certain bundle of null rays. And there's an area to that aperture of the telescope. So when you build SALT, you've got a nice big area compared with all the old telescopes sitting up on the hill at Sutherland. You're chopping off a much bigger solid angle from the light which came down here. And what we can define here, we can define dA is rg squared d omega g. This is exactly the same formula as we had before, but that one was applied to the downgoing null geodesics, and this is applied to the upgoing null geodesics. So you've got the null geodesics which spread out from us, or at least which are arriving at us from all places down below, and you've got the null geodesics here spreading out from one particular object down there, spreading out in all directions. The light from that object has spread out into a huge sphere, and we managed to intersect a tiny little fraction of that light from that object. With just a little bit of thought about photon conservation and so on, you can work out that the luminosity, and the formula is given somewhere in here, the flux we receive up here is equal to the luminosity over 4 pi, 1 over 1 plus z squared, 1 over 1 plus the scale factor squared today, times f squared of r. And that is the flux we receive from down there. This is basically based on photon conservation, that every photon emitted into there is received up here. And there are two factors, 1 plus z, which come as follows. Firstly, photons are being emitted at a particular rate down there by the source, the sun, the galaxy, whatever. But because of redshift, I emphasize redshift is a time dilation effect. We receive these at a factor slowed down by 1 plus z because of redshift. So that's the first factor, 1 plus z. The second factor, 1 plus z, you have to work at a bit, but it's easiest to think of it from a quantum viewpoint. You've got a photon which sets off a particular frequency here. It arrives at a lower frequency here. You lose energy in the photon because of the redshift affecting the frequency. That's where the second factor, 1 plus z, comes from. And this is the area factor saying that the light that went into a solid angle d omega there is received in a solid angle d up there. And this is the basic of the magnitude redshift curves. From this, the magnitude is a logarithmic measure of the flux, and the redshift is there. So if you know the luminosity of the source, and you substitute, now this is what we've called rg squared. And if you think about this one here, this here is the same as this here, excepting this scale factor is evaluated at the time of emission, and this scale factor is evaluated at the time of observation. And what that means is that Rg squared is Ro squared into 1 plus Z squared. I hope I've got the square the right way up in that. And what that means is that the downgoing and the upgoing area distances are the same up to the factor 1 plus Z squared. And this is what Bruce Bassett was talking about yesterday, that the downgoing null geodesics and the upgoing ones are tightly correlated by what is called here the Reciprocity Theorem. And the Reciprocity Theorem says, if you know how areas work going down, you know how they work coming up, because they are simply related by a factor 1 plus Z squared. So these are the three basics, and then the final basics is numbers. And what you do in a particular part of the sky, you look at a photographic plate or a CCD image or whatever, and you count the number of sources you see there. This goes back to Hubble. This is what Hubble was doing in 1934, and it's how he first showed the universe is approximately spatially homogeneous. So the question is, can we get a formula for the number of galaxies that we will see? Now the problem is, this is an integrated set, and what you really want to do is the following. Now we're looking down from the source, and we're looking down, and we're looking at a little volume down the light cone. And that volume may go from a redshift Z to a redshift Z plus dz, for instance. So in other words, that will correspond to dz. It'll have a certain volume, dv, and you can calculate that volume because you know that area, and you can easily work out what that distance is. And so what you can work out is dn is some function times dv, and then dv is minus, it's the redshift actually, the scale factor times the area distance times the increment in redshift. And the details are written down in those notes I've given you, so I'm not going to bother with those details now. The point about it is the following. We can theoretically write down a number there, provided we know the number density of galaxies. So if you know the number density of galaxies, you know the volume. dn is the number density times the volume. And that's the number of galaxies which you should see between a redshift of Z and Z plus dz. So you can plot these curves of number densities as a function of redshift. And then you can go out and look at a plate and try to count the number of galaxies or radio sources or X-ray sources, whatever they are, and use number counts. And that's the third kind, the fourth basic thing. Redshifts, angular sizes, luminosities, and numbers. Now, we could go into a lot more detail about all of this. In a sense, I will be summarizing the outcome of this afternoon when I talk about the concordance model. But there's one thing which I would like to just say a little bit about, because from here to here, I've made a really big assumption which is not true. What I've assumed is that the number of galaxies there is the number density times the volume. That is true. What is the false assumption? The false assumption is that when you look at the photographic plate, you see everything that there is in there. And that is not necessarily true. We may easily not see all of the galaxies in that volume. I'm now talking about page 129 in these notes. What we need to add in here is a factor p, which is the probability that you will detect the galaxy. Now, you may not detect it, or you may not recognize that it is a galaxy. And this is where life gets really interesting, because there's all sorts of selection effects and detection effects which come in to whether you see a galaxy and whether you recognize that it is a galaxy. And I just want, some of the mathematics of this is written down in those notes. I just want to show you the basic kind of idea. And the starting point is the following question. If you look out at the sky there, where are the stars? Okay, you don't see the stars. Where have they gone to? Where are all the stars in the day sky? Well, they're there. You just don't see them. Why do you not see them? Let's take brightness as a function of angle in the sky. Here's a typical galaxy image. The typical galaxy image depends on the profile of the galaxy, but a typical galaxy image, it'll have a very bright center, and it dies away.